Ever seen the movie 2012? Well, not something like that, but in the longer term, you can speak of something like that. Now, we're joking, of course. In today's episode, we are here to speak about certain variations in the first and second degree gravitational harmonics of the Earth. Confused? In short, the geocenter of the Earth is changing. Well, that sounds concerning, doesn't it? Let's see. Hey folks, welcome back, and you are watching Skies TL. What are you guys waiting for? Like, share, and subscribe. We all use navigational apps on a regular basis. Most likely, you will be using an app that uses GPS to locate your exact location on Earth. What you may not realize is that underlying your favorite navigation software lies an invisible architecture of systems that work together to provide you with an accurate position, and that the cornerstone of these systems is a TRF or terrestrial reference frame. So you might be getting that the TRF is based on a precise determination of the geocenter of the Earth, which is essentially the Earth's center mass. One issue is that the geocenter is continually shifting in relation to the Earth's surface. Scientists can compute where the geocenter of the Earth is at any given time to a few millimeters using a network of ground stations equipped with telescopes and lasers that shoot pulses at certain satellites. As a result, a reference frame is essential in any mapping, location, positioning, or navigation application. What we have here is that this geometric center of all land surfaces on Earth, or the superficial barycenter of the mass distribution produced by treating each continent or island, is being altered. So what exactly is this happening? Despite our orientation to thinking of Earth as a static entity, it is in fact a dynamic and ever-changing dome. The terrain is eroded and shaped by wind, water, and ice. Volcanic activity and earthquakes change the Earth's geocenter in spectacular and often destructive ways. On a far longer timescale, the movement of the Earth's plates gradually reconfigures seas and continents. Each one of these processes has a role in the Arctic and Antarctica. Water covers nearly 70% of the Earth's surface, rendering it inhospitable to humans. The 30% of the Earth's land surface covered by land surfaces is spread out in an unusually shaped array of continents and islands, all of which are either inhabited or potentially livable by man. 3 of the 7 big continents, as well as 2 more, are genuinely connected. Erosion is one of the causes of this. Wind, water, and ice are basically the 3 main factors responsible for erosion, or the removal of rock, sediment, and soil. Weathering, the physical or chemical disintegration of minerals in the rock, is distinct from erosion. Weathering and erosion, on the other hand, can occur together. Erosion is a natural process, but it is often accelerated by human activity on the soil. Deforestation, overgrazing, development, and road construction all expose soil and sediments, resulting in increased erosion. Excessive erosion causes soil loss, ecological harm, and silt accumulation in water sources. Erosion can be reduced by constructing terraces and planting trees. Well, erosion wasn't just the one that washed away everything. The sea level was lower during the glacial epoch, and a land bridge across the Bering Strait connected Eurasia to the Americas. A land bridge between the Malaysian peninsula and the Indonesian islands may have connected Australia to Asia. A major portion of Earth's mass lies in the Arctic and Antarctic. Glacial erosion has altered much of the terrain in the Arctic and subarctic. Glaciers degrade largely by plucking and abrasion. Plucking happens when a glacier runs over bedrock, softening and lifting chunks of rock transported into the ice. Because of the strong pressure at the glacier's base, part of the ice melts, generating a thin layer of subglacial water. This water seeps through bedrock fissures. When the water refreezes, the ice serves as a lever, lifting the rock and freeing it. As a result, the broken rock becomes part of the glacier's weight and is carried along as the glacier advances slowly. Glacial erosion may be seen in the U-shaped valleys and bays found across the Arctic and subarctic areas. Glacial moraines arise as a glacier recedes, leaving enormous mounds of rock, gravel, and sometimes boulders behind. Moraines can occur at the glacier's foot or sides, or in the center of two merging glaciers. Coastal erosion has been a big concern in the Arctic in recent years, with Alaska's North Slope losing up to 30 meters or over 100 feet every year. Can you believe it? The main reason is assumed to be climate change. As the temperature warms and sea ice melts, ocean water absorbs more of the sun's energy. As this heat is transported to the land, the permafrost, which is simply frozen soil, warms up, putting the shoreline vulnerable to erosion from wave action and storms, which are becoming more common as temperatures rise and the open sea expands. In fact, when the winds play a huge role in transporting mass from one place to another, katabatic winds have a significant effect on erosion in Antarctica. This form of wind arises when high-density cold air accumulates at high elevations such as atop ice sheets and travels downwards due to gravity. Katabatic winds in Antarctica and Greenland are very cold and rapid, frequently approaching hurricane force. Small grains of sand carried by the winds in Antarctica scour and erode the exposed rocks, resulting in strange patterns and formations. Ventrifacts are usually formed eroded rocks. If you want to learn more about this geocentric shift, one must look more into the tectonic plates. Plate tectonics explains the movements of the Earth's lithosphere, or the outermost layer of hard, solid rock over geologic time. Scientists can learn a lot about the past of the polar regions thanks to plate tectonics. The lithosphere of the Earth is divided into 7 major and numerous smaller tectonic plates. These plates shift in respect to one another, gradually shifting the position of the Earth's continents and seas. Geological data from Antarctica supports the notion that North America and Antarctica were formerly united in the global supercontinent Rodinia some 1 billion years ago. The continents gradually separated, only to rejoin some 200 million years ago as the supercontinent Pangaea. Fossil evidence from this time period reveals that Antarctica was linked to Australia and South America and was much warmer than it is today. Because of the movement of the tectonic plates, this shift is linked to most of the world's volcanic and seismic activity. The majority of volcanoes form near plate borders when two plates are moving apart or together. A few volcanoes, such as the Hawaiian Islands, originate as a result of a hot spot or a weak region in the Earth's crust when magma makes its way to the surface. This is a fine way of mass action on Earth. So we now know that the Earth's form is continually changing and that land masses are always shifting. It's at low levels, so it's not something you would feel for yourself. As a result, we are continually monitoring what's going on with the Earth as a whole and the Earth's surface. To do this, NASA and international partners monitor measurement sites located across the world to identify where, how much, and in which direction our planet is changing. Because the Earth's surface is constantly changing, any measurement is not in a fixed coordinate system. It must consider the fact that it is tied to the landmass and where that landmass is at any given time. And like a coordinate system drawer on paper, the TRF has an origin, or in this case, the central mass of the Earth known as the Geocenter. As a result, many Earth-observing satellites orbit around the Earth's center mass rather than its geographic center. As a result, pinpointing where it is crucial for scientists to ensure that our Earth measurements are reliable. This data is utilized to create higher-level goods, geodetic products, that may be used by NASA missions for a variety of scientific applications. NASA cannot accomplish this alone since it is a worldwide measurement. We rely on the worldwide community to provide all of the data required for global coverage. Anyways, we'll be facing more issues regarding the mapping of the environment due to this geocentric shift. So, coming to the end of the video, Did you love today's episode? Anyways, drop in your ideas about what's happening with our Earth's geographical center in the comment section below, and also if we have missed out on any information. This isn't the end of the story. More interesting stuff will come up in the coming days, and we here at the Skies TL will deliver the best of the content to you folks. That's about it for today. Make sure to subscribe to our channel for more content just like this one. And while you are at it, turn on post notifications so that you never miss out on any of our future uploads. Drop a like for the video if you are a massive fan of space-related stuff. Hope you enjoyed the video. We will meet again in the next one.